So now we're ready to continue on with problem 6 and problem 7. Number 6, we're working with gold. Now gold is not water. So if gold was at negative 20 degrees Celsius, what phase of matter would it probably be in? Well, we're looking at probably it would be in a solid phase. So if this was gold, the actual boiling point of, the melting point of gold, I don't really know what that is. Let's just take a quick look and see. So if we go over here, just what is the melting point of gold? Looks like it's 1,948 degrees Fahrenheit or 1,064 degrees Celsius. So if we go back here, we can see that gold will have a melting point that is significantly above the temperature in this problem. So at 75 degrees, gold is certainly going to be a solid. So if it's a solid and its temperature is changing, we would use the Q equals mCp delta T formula because we use this formula anytime the temperature is changing. So what is the mass of the gold? It's 500 grams. We know the specific heat capacity of gold because they gave it to us up here. I don't know if you noticed it or not, but right here it tells us. So it's 0.129. Notice that compared to water, it's like 40 times less. So it's way easier to raise the temperature of gold than it is to raise the temperature of water. It has a low specific heat capacity. Remember the skillet versus the plastic? Gold is more like the skillet, and water was more like the plastic. Water had a high heat capacity compared to the gold. All right, so over here we'll go ahead and put in our heat capacity. It's 0.129. And that was in joules per gram degree C. And then the change in temperature that we're dealing with in problem number 6 is from negative 20 to 75. Well, how far is it from negative 20 to 75? So if you think about a number line up here, here's 0, negative 20 is over here, 75 is over here, so that's 75 degrees here plus 20 more. So you go from negative 20 to 0, then 0 to 75, so you really have a 95 degrees temperature change. So now we're ready to multiply. Notice grams cancel, degrees C cancel, and I'm just left with joules for a unit. And the actual numbers will be 500 times 0.129 times 95. So I get 6,127.5 joules. If I wanted to change that to kilojoules, just put joules and kilojoules, 1,000. So you'd have 6.1275. Whoops, not 1275, which I'm just going to round off to 6.13 because that 2 is followed by a 7, so 6.13 kilojoules. All right, so that was number 6. Number 7. Number 7 is a problem that requires you to think in these terms, like on the video that I made yesterday that dealt with phase changes. So we're going to heat this sample of water from 23 grams, starting at a temperature of negative 46. And we're going to end actually at 109. So we're going to do this in steps. And then we're going to calculate the total energy needed, which doesn't ask us to do that, but we're going to do that anyway. All right, so if we wanted to look at where's 46 on this graph, remember water had a melting point or a freezing point of 0, or a boiling point of 100. So where is negative 46? Well, it's down here somewhere. So our first step in this process is we've got to get the energy, we've got to find the energy that it takes to get from negative 46 up to 0. So I'm going to do that here. Q equals mCp delta T. So we have the mass in this problem was 23 grams. That's going to remain constant all the time. The specific heat capacity, we have to use the specific heat capacity for solid water, so it's 2.06. So we'd have 2.06 joules per gram degree C. And then the last, the change in temperature, we're starting at negative 46, and we're going up to the freezing point, which is 0. So we're going to need to have a 46 degree temperature change. So this number right here will be 46 degrees C equals. So the first question here, the energy that it takes to get up to 0 degrees, is going to be the product of these three numbers. So let's go ahead and do that. We'd have 23 times 2.06 times 46, 2,179 joules. If I'm doing this in sig, I'm not going to do this in sig figs, I guess. But if we did, we need three sig figs, because these are to the tenths of the gram, and so that would be 23.0. That'd be 46.0, and so we'd have 3 sig figs. But we'll just leave it at 4 for right now. All right, then moving after we get to the freezing point, you know from the video that I showed you yesterday with the ice in the pan, we know that when we heated the ice, the temperature didn't raise until the ice was all melted. Now it wasn't perfectly displayed in the pan demo because of I couldn't get my thermometer right in the middle of an ice cube. But in a perfect world, temperature doesn't change while it melts. So, but you're still heating it. So we have to use the formula Q equals mass times heat of fusion. Remember, down here we have Q equals mass times heat capacity times change in temperature for this space. Now Q equals mass times heat of fusion. So the mass is the same as it was previously. And the heat of fusion we calculated at the start of the previous video. Somewhere, here it is. The heat of fusion was given to us in kilojoules per mole, and we calculated it in joules per gram. So it's 334 joules per gram. And that was in grams. So what's going to happen is you're going to cancel grams, and you just end up with joules. So you have 23 times 334, 7,682 joules. Oops, joules. So now we've crossed here, and we're ready for the third one. That's how much it took to melt the ice. Would be that 7,682 joules. Now we're going to heat the water from 0 to 100. So if we're heating from 0 to 100, we're going to need it as a temperature change again. So we're going to use this formula. Q is equal to M Cp delta T. So Q equals M Cp delta T. M, mass never changes, 23 grams. The specific heat capacity is 4.18 joules per gram degree C. We've used that previously, but in case you're wondering about that, right here, 4.18. And the change in temperature from 0 to 100 is 100. So doing the math, you'd have 23 times 4.18 times 100, 9,614. So now we know how much energy it takes to get from here to here, given 23 grams of water. Now we need to cross this line, and this is the boiling line. Now remember, for boiling, the quantity of heat is equal to the mass times the heat of vaporization. So I'll go ahead and show that calculation right here. Q is equal to the mass, which is 23 grams. The heat of vaporization we calculated at the beginning of the previous video, 2,260 joules per gram. Again, there is no temperature change while it's boiling, so you have to use a formula that does not have temperature change in it. We have 23 times 2260, 51,980. It's a lot of joules, but that's how much energy. It takes a lot more energy to boil something, see 51,980, than to melt something, 7,682. And so that's no big surprise. And now we're ready to do our final calculation, which is calculating the heat that it takes to get from 100 to 109. So now we have a temperature change again, because 109 will be up here somewhere. So you're going to use the formula that has temperature change in it. Q equals mCp delta T. Mass, again, is 23 grams. The specific heat capacity, since we're in steam, we have to use the specific heat capacity of steam, and that is 2.02 joules per gram degree C. So 2.02 joules per gram degree C. And the change in temperature here is from 100, that's 100, and that's 109. So from 100 to 109. So that's a 9-degree change. So grams cancel again. Degrees C cancel. You just end up with joules. You have 23 times 2.02 times 9. And that's 418 joules. Okay, so now that answer would be 418. So answer to question A was 2,179 joules. So it takes 2,179 joules to make this temperature change. Then we have to melt the ice, and that took 7,682 joules. To raise the temperature from 0 to 100, that took 9,614 joules. Then to boil the water, we needed 51,980 joules. Then to raise the temperature on up to 109, it only took 418 joules. So if I wanted to know the total energy change that it takes to make 23 grams go from negative 46 all the way up to 109, all we would need to do is add the numbers together. So you'd have 2179, 7682, 9614, 51,980. That's the biggest by far. And then 418. So if you add those together, I'll just do it on a calculator and be lazy. We'd have 2179 plus 7682 plus 9614 plus 51,980 plus 418. So 71,873 joules. Which is 71.8 kilojoules. So that's how much energy it would take to raise the 23 grams of ice. And 23 grams of ice would be about the size of 23 M&Ms. Take the 23 grams and raise it from ice in your freezer at negative 46. That would be a really, really cold freezer, colder than yours is. And it would raise the temperature up to 109 degrees. So it would be steam at 109 degrees. It would take 71.8 kilojoules. And if you want to just, this is extra, but if you want to change that to kilocalories, kilojoules here, kilocalories here, 1 calorie is 4.18 joules, so 1 kilocalorie would be 4.18 kilojoules. So you take your 71,873, divide by 4180, and that would be 17.2 kilocalories. And a Milky Way bar has about 250 kilocalories. So 250 divided by 17 would be 14.7 times. So it would be you'd about 1/15 of the size of a Milky Way bar. So if you divided a Milky Way bar into 15 pieces, that'd be about this much energy. All right, so that's a little overview of how to do calculations on phase change problems. And I'll throw up some practice ones for you to do.